All right, hello everyone. So this is a video going over the Rocketry 101 meeting. So a couple weeks ago we held a meeting basically explaining at a high level how rockets work. So when when you got a complex thing like a rocket, like there's a lot of parts on it. This is only half of one, but like you got fins, you got the rail lug to attach it to our launch pad. You got lines that connect the parachute and the different stages of the rocket together. And then there's our custom 3D printed parts. And then there's gonna be a motor and a parachute and like a little computer. And like there's quite a few things. So how it normally develops is eventually there's a portion of the rocket that you're like quote unquote in charge of. Be it like this component right here, or be it figuring out how to get our parachute to come out smoothly and effectively each and every time the same way. Like eventually you will specialize, and that's the normal thing to do, and that's the best way to do things the vast majority of the time. But the problem with specializing is then you can lose yourself in the bigger picture. So you can lose track of how your part is going to fit into the rest. So you optimize things. A good engineer optimizes parts. So therefore a good engineer will make the best part, but maybe the part is no part, or you'll lose track of what the exact objective is. And that's what this whole meeting is supposed to do. Make it so that way everyone understands how their work fits together, so that way you guys can start to learn systems engineering, which systems engineering is getting parts to work together through a mixture of management strategies and just general design intent ideas and communication and other things. And then just the general like actual engineering side where it's just like, making things work well together. So that's what this video is about. I'll pop in and out with segments shot after the fact, so that way you guys can get things a little bit more concisely. Thanks for watching this, by the way.
Let's just draw a rocket first. All right. So your first part is, let's just start off with a top-to-down survey of a rocket. Okay. So what we call this part, we typically like to divide this off, and this is called the nose cone. And so what the purpose of a nose cone is basically to cut through the air. So basically what happens is as the air flows around the rocket, we want to have as minimal amount of impact on the airflow as possible. And so this can be accomplished through a rounded, like a slightly sharp rounded top. And this basically prevents drag from basically counteracting the force of thrust on a rocket. So we will cover the aerodynamics of that later on. But the next part, the main body of a rocket, is going to be called the fuselage. And so this is basically the tube that houses most of the rocket's components. And here at Astral Orbit, we typically like a clear fuselage. We use a material called polycarbonate. It's a plastic, and it just allows for ease of inspection and maintenance. That's all there pretty much is to the fuselage. It's just like a structural component that holds the rocket together. And so next, what we have here is a parachute. So obviously, we don't want...
So I'm going to explain a couple physics things really quickly. So position, that's your position. So like this is just some basic physics stuff. Let's say we're tracking the motion of this game controller. So position is where it is horizontally, vertically, yada, yada, yada. That's position. Then you got velocity. That's the speed that something is going at. Then you got acceleration, so velocity is the rate of change of position. So how fast is it moving left or right, up and down, forward, backwards, etc. Then acceleration, what that is the wait, that doesn't matter. I was thinking about the calc side of it. So then you got acceleration, which is the chain of the velocity. So if it's speeding up, so then you can have what's called negative acceleration, which is where you're slowing down. It doesn't mean that you're going in the negative direction. It just means that you're slowing down. Eventually, you might start going in the negative direction. That's not really relevant to this conversation. And terminal velocity is the maximum speed that an object can travel in free fall motion. So let's say we got something falling. You got gravity pulling it down. You got drag pushing up because it's resisting that, sort of. So terminal velocity is achieved when the force of drag equals the weight force, causing it to no longer accelerate downwards. So we'll just travel at a constant speed downwards. A rocket will go very, very fast downward. Its terminal velocity is very, very fast if there's no parachute or if the stages don't separate because it's so aerodynamically smooth. So that's a little add-on.
Our rocket to be flying at terminal velocity down onto the ground and potentially injuring someone. This has happened before. We've had some close instances, but typically you want to slow down the fall of a rocket. And so what a parachute does is, and you have that, okay. So when it's deployed, what happens is it comes out of the rocket, right? And this can be accomplished by a variety of means, but
it's generally ejected by the motor around. So within the motor, there's a small charge called the ejection charge. So after the motor burns, which is like for like just over a second, there's a little material burns, which acts as like a timer. And then a small explosion happens actually inside the rocket. Not like the stuff that pushes it up, but inside of it. This separates these two sections of the rocket, so the parachute can come out and fill up with air and then slow it down, so it can come down safely.
Yeah, so that's what happens. And so the parachute, when it comes out, it basically traps the air that's under it. And so what that happens is it increases the coefficient of drag, and thus it creates a force on the rocket upwards that counteracts the force of the gravity on the rocket, or the weight. We call this drag. And so what happens is that the terminal velocity, or the velocity at which the drag force equals to the weight force, becomes much slower and allows for a controlled descent. So that's that. Then we have the fins. And so the main purpose of the fins is just to stabilize the rocket. They basically provide a large surface area, right? That when air flows around this this area, basically it prevents any sort of wiggling or deviations from upwards, which is what we generally want a rocket to point for most of the flight. And what happens is that the air moves around it, and then if it's like, let's say if the rocket was pointing to the left, right, a little bit.
This explanation is a lot easier when you have a rocket in hand than it is with a 2D drawing. So I'm just going to explain it real quick. So let's say we have rocket here. So eventually what's going to happen is some amount of wind or some other horizontal force is going to hit the rocket. This will cause it to rotate around the center of mass, which on this rocket, which would be about right here. Imagine the rocket's a lot taller. The wind is going to hit it, and it's going to rotate from this side. Let's say it just rotates this way, okay? What's going to happen is this is going to cause the fin to become more exposed. So now I'm going to explain how drag works. So first I'm going to explain how the equation for drag. So you got a coefficient in front of it, which is just a number based off of the shape of the object. You got projected surface area. You got velocity. Those are the things that affect drag generally. I might have missed something, but for this conversation, that's what matters. So projected surface area, what is that? So I am holding a fin right. So I'm holding a fin right here. So you can see how many pixels it takes up on your screen. It's about that big. But you notice how as I rotate it, it appears to get smaller. It's not getting smaller, but there's less surface area exposed from your perspective. This is projected surface area. It's basically area from a perspective, and that's what's important for drag. So let's say the rocket gets a sideways force. Oh no. You notice how more of the fin got exposed to that perspective? So that's going to cause it so that way that drag force is going to cause it to correct that way, and it'll oscillate and then go straight again. So what the rocket is constantly doing is oscillating left and right, left and right, left and right, just a little bit until it gets perfectly straight. But in reality, it's always oscillating just a bit. Even if it looks straight to your eye, it is oscillating just a bit. So back to Andrew.
Purpose of the motor is basically to create thrust. And so what is thrust? Thrust is basically it's basically a force that pushes up on the rocket that causes it to accelerate upwards and counteract the force of gravity on the rocket downwards. And so what we basically have, this is called a thrust curve. And so each motor it's basically, if you took a cross section of this motor, right? What happens is there's a channel full of air, and you have this side sections that are full of propellant. And so what happens in a motor that we typically use, which is called a solid rocket motor, we have a solid propellant. And so basically it is a mixture of ammonium nitrate, which is, as you can see, has a lot of oxygen in it, with propellant, which I don't know in this case. And so this propellant just basically reacts with the oxidizer, and then it creates a combustion reaction. You may know it as like, in general terms, like burning a fire, right? What happens is oxygen is reacting with, for example, wood, and that causes it to release energy. And so what happens is this energy gets converted into kinetic energy by expelling gases that are a result from this reaction. So what happens is, for example, carbon dioxide or water, which is a result from the combustion reaction inside here, it gets forcefully expelled out because of the energy of the reaction. And so by Newton's third law, which is that each force has an equal and opposite reaction, since the motor is pushing this reactant mass out, what happens is that this also exerts a force back up on the rocket. And so this is the premise behind the thrust of a rocket.
Do you need the thrust curve anymore?
Yes, I still need that. I'm going to get to it. And so as this sort of burns off, the inner sort of this channel of air here, right, it tends to like get expanded and like it becomes smaller, right? And so the result of this is that since there's altering amounts of surface area inside this chamber here, what happens is that the thrust of the motor initially starts high, and then it starts to decrease and decrease. So the thrust produced by the motor is decreasing as time goes on. And this sort of curve varies depending on the motor, its design, and stuff like that. And we can get into that later.
This one?
Hold on, let me check. Okay. So if you look at the thrust and versus time curve, what happens is that if you take the area underneath this curve, which is called an integral, you get what's called an impulse, which is basically the total amount of thrust that you're going to be putting out over time, right?
Yeah, so most of the time when we're actually like doing this stuff, we're not usually doing the hard math of like actually calculating, okay, how much force is it applying at this time? We generally just make computers do that stuff because it's a lot quicker and a lot easier and a lot more accurate most of the time. But what's important to understand is, so at different points in time, there's varying amounts of thrust. So right at the start, there's a big burst, and then there's a long sustain, and then it stops burning. The rocket's in the air for like is going upwards for, I want to say like 10 seconds or so, but only 1 second is it actually burning. So the important part is it burns for a very short period. The amount of force changes throughout it, and you can actually classify. So most of the time when you're looking at motors, you do look at the thrust curve, but at basic level, you usually just look at the motor code. So can you write that? So
okay, so motor codes. You first have a letter, let's call it X, and then you have a number 1, let's call it that, and then dash, another number. So this, I believe this is the impulse class, right?
So so there are ways that you can classify motors. The first letter is like how much general impulse there is. So it'll be a letter starting from A all the way to like O. We generally fly with Fs. Each letter is a doubling in total impulse, so like a doubling of total power coming from the motor. So, but that doesn't tell you the exact number. You have to look at the thrust curve to find that, but that gives you a very rough idea. The second number is your average impulse, or the average amount of thrust that's applying over the time. And then the last number is how long until after the motor finishes burning. Actually, no, after the motor is lit until there's the ejection charge and the rocket separates.
So yeah, so basically at the top of a motor here, what happens is that there's a little section here. and there's a little bit of stuff that gets burnt as after it gets lit. So when it starts to burn, right, this part also starts to burn, but a little slowly. And so the width, the height of this little section can control basically how long it is before the ejection charge fires. And so what an ejection charge is, it basically has gunpowder in it, right? So after this gets burned all the way through and reaches the gunpowder, this cap gets pushed off through an explosion. And that also releases a bunch of hot gas, which is basically how a gun works, right? Hot gas accelerates a bullet across a barrel. The same thing works for here. As this gas expands inside the fuselage, the motor, the parachute, and by extension, the top half of the rocket comes off. And that allows for the parachute to come out. So that's basically what this little number here means. I think that's all for motors, right?
Yeah.
Okay. Finally, let's talk about aerodynamics. So, are you guys aware of center of mass? Okay, if you know that, okay, let's go.
So just that way everyone knows, center of mass is basically the point where you can balance something. And then you can treat it as if all the mass is there in most situations. I won't dive into it.
Okay, let's call this the center of mass. Let's just make it be right here. Okay, and this is basically the center at which the rocket will pivot if any sort of forces try to like pull it sideways or anything. Then you will have your center of pressure, and this is modified through the shape of the fuselage and the fins. And so generally what we use for the fins, as I explained earlier, what happens is as the air presses onto the fins, it puts like an angular momentum on it. And so what happens is the larger the fins, the lower the center of what we call pressure. So typically, the center of pressure is going to be near the fins because that's the big surface area where the air will sort of meet, right? And so what happens is you can alter the position of the center of pressure by basically increasing or decreasing the size of the fins. We typically want it to be a medium ground because if it's too close to the center of mass, what happens is that the rocket becomes unstable because the correction of the rocket's course from the air becomes less substantial, I guess. But if it's too far away from it, the angular force that any sort of pressure will exert on to the rocket, it becomes too stable. So, for example, if there's a wind, for example, let's say there's wind, right? What happens is that the rocket is called what we call overstable, meaning that any sort of like air currents will cause it to like move sideways a little too much. And that's not what we want. Because in TARC, basically what we're trying to do is to reach a certain altitude. And so we neither want too large a fin or too little a fin, right? So that's basically the premise behind fin design.
So then so this is measured in stability. There's a more technical way to do it, but I'm just going to use the term of stability. So the more stable a rocket, it's not like, oh, stability is good. Stability is just a measure of how much the rocket will react to sideways forces, basically, from wind, more or less. So if you have a rocket where it's very close to it, where it's a stability of, I believe, 0.5, doesn't matter, but it's just a stability of 0.5, it'll go straight in the direction of wherever it started. It won't correct, it won't do anything. Once you get to about 1, it'll correct a little bit. And then once you get like above 3, it's just gonna correct a lot. So it's not like more stability nor more better, it's more stability, more correction. So then you have to actually factor it into other things, but that's a lot more in depth and we haven't figured that out too much. Another thing to say is if you have like no stability, if an outside force acts on it, it'll start to shoot in sideways. So that's why you want to have some amount of stability and not just rely on no wind. So.
As he said, we want the rocket to just keep going straight after the launch pad, right? And so what many rockets do, specifically model rockets, is they have a stability enhancing device from the launch. And so what we have currently is what we call a launch rail. And so what happens is there's a little like jut out from the rocket that can interface with a launch rail.
I'll draw that for you, bud.
So the launch rail, what we do is basically have it go up like that, I guess. And so what happens is that this little, what do we call this thing?
This is a really bad drawing, but what this is right here is the launch rail. So this is where the rocket starts on. It slides into this. This is like a top-down profile of it. You have the rocket launch lug right here. It slides into the rail, and the rail is just a long, tall pole, like you see right there. And the purpose that it serves is drag only works if you're moving really, really fast. So when you start the motor, you have zero velocity. You're not moving very fast. So you need time to build up velocity, build up speed, so a drag can act on the rocket, so it points straight. Because then what can happen is, if you just launch with no rail, it could just go sideways. It could, who knows what will happen. We use a very long launch rail, so that way we just don't have to worry about it as much. So we have a lot of time to build up speed.
Yeah. And so one metric that we use, we commonly use, is called off-the-rail velocity. And so typically, that's when this lug, when it comes off, the instant it comes off, the velocity at which the rocket is going is what we call the off-rail velocity. And so, as he said earlier, the faster you're going, basically the more chance that the rocket has to like readjust itself due to pressure from air. And basically the higher it is, the more stable, the more straight it will be when it comes off. What else? Can you talk about motor holders?
Motor holders?
Yeah.
Okay.
All right, so I'm just going to show you guys what the CAD diagram actually looks like. So here we have the motor holder from a couple years ago. So how it works. So first of all, first step is we slot the motor into the motor holder itself. So there's this hole right here. That will be touching, where did I put it? I just, oh, there it is. They'll be touching this surface right there, that inner surface. And then what happens is this surface right here is getting pressed up against this. So that when the motor is under thrust, it's getting slammed into that, which transfers the load to the rest of the rocket. So then that load gets transferred through the part to this lip right here. That little lip bumps up against that lip right there, causing the rocket to go up. So then when we get to around apogee, the ejection charge fires. And the ejection charge is going to want to shove the motor right out the bottom, which is real bad. So what we do is we've done one of two things. We've had a retainer. You can see a retainer right here. So it would get slotted, retainer right there. It would get slotted on this hardware right here. It's a little complex. And then it would make it so it can't go any further because it would bump into the retainer. The solution we've been using lately, which is a lot simpler, hence why we've been using it, is we've been putting tape around the rocket motor right here. A big clump of it, a big wad. So that way when it tries to get ejected out, it just can't because it's going to bump into the tape. And then we take off the tape post-flight. That's it for motor holders. Back over to Andrew or myself, whoever's talking.
Now I'm just going to go through the rocket anatomy from like a structural perspective, and then we're pretty much done actually. So in the rocket we went over how we got the parachute, we got the nose cone, we got the tubes, we got the motor holder, and then we got the launch lug. Did I miss anything? Okay.
Fins.
Oh yeah, how did I miss fins? That's kind of funny. So how we attach fins is you want that to be a very strong connection. So we use what's called epoxy. So here's a side profile of it. So here's the body tube. Right here we have the fin. So we glue it right at this little junction, but that is not very strong. That's pretty weak. What you want to do is you want to increase the surface area. So we put what's called a fillet. It's basically a rounded surface that fills in that area, and we fillet it with what's called epoxy. So what we do is we basically just are putting a bunch of epoxy. I'll link a video on Discord to just show that process.
Could you actually, I'll explain what epoxy is, right?
It's basically just a two-part glue that's very, very, very strong.
So what happens, I'll just have to teach this because you have two chemicals. You have a binder and a
That's not
a
really
structure,
relevant
right?
for this conversation.
So basically what happens is that when you mix it, it creates like a chemical structure that makes it like solid, and that's what we call curing. And so it takes a little while for the epoxy to cure, but basically you just apply the two parts onto like where you want to glue it, and then you slap it on, and then like
Yeah.
you have to like wait a little bit because it has to cure and set. So in order like for it to become solid. That's what epoxy.
So next up, the rail buttons. So we used to use what's called a launch lug, which would just be basically a very long thing that would stick into it. So you see that profile right there? Just that, imagine that, but like extruded up like an inch or so. But then we recently switched to what's called rail buttons. So basically just imagine that profile, but it's like circular. So imagine like a screw type thing that's like slotting into there. And then there's two of them. So there's one that's at the center of mass. So we'll just pretend like that's aligned. And then you put one as close to the bottom as possible. The reason you do that is so that way you want to be aligned with center mass, that way so that way it's just strong, and then you want as low as possible, so that way it's on the rail as long as possible. Because if it's up here, if there's only one rail button, when there's only one rail button on it, it doesn't do anything. So you need to have two, so you want one to be as low as possible, and then one there.
Basically, it gives you 2 points of contact across the fuselage, and that just keeps it so like it's like angled upwards.
Yeah.
Precisely with the rail.
Most of the other parts on there are friction fit. So we have the main body tube, and then we just like slot in the foam nose cone, and it just like sits in there from friction. So we're going to be doing two main rocket related projects this year. So we're going to be doing what I'm just going to call fun rockets. So we're going to be starting to do some high power rockets because we have so many people this year. We don't quite have, and we don't have the resources to run 2 TARC teams, but we would really like to put some time and money into just building more fun rockets. So stuff that goes really high, maybe 2-stage type stuff. Who knows, just stuff that includes like flight computers. And then TARC is our main competition that we've done historically. So TARC is a national rocketry competition in the United States. I don't know why. So in TARC, the goal is to launch a custom design model rocket as close to a height as possible. This year it's 850 feet, I believe, within a certain time period while carrying an egg and not breaking the egg, because for some reason science competitions have a fascination with eggs. Not totally sure why. And that's our main competition. That's a 10-person team. We'll be doing some mock TARC launches, so that way we can just get a bunch of people, get some flight experience, see if they enjoy this and just see how people like it, and then we can go from there.
I also just want to say that we're doing mock TARC flights mainly as a way to onboard people, because we've done TARC flights many times. We've done easily 35 of them. So this is a process that experienced team members are very familiar with. So by doing them, we can just focus on teaching you guys the process of doing a TARC flight. And TARC flights, the general process applies to almost everything. So that's why we're doing that.
Yeah.
So I hope this was useful. Thank you guys for coming. If you need to talk to me, Andrew, or Shyam, that's it.